So today we're going to be doing the second part of the May-June 2025 paper 12. In the first part I solved the first 20 MCQs, and today we're going to be starting with the 21st MCQ. A reaction occurs when ammonium chloride is added to calcium hydroxide. What is the role of ammonium ions in this reaction? No worries, we're going to write the equation, we're going to look at what's happening and then figure it out. Ammonium chloride is NH4Cl. And you know that ammonium ion is a very good acid because ammonium ion can donate its extra proton and convert into ammonia. That's why ammonium ion is an acid. And then we're adding calcium hydroxide to it. And what we're going to form is, that whenever we have an ammonium salt, that's a reaction that was part of O-levels IGCSE, that you have a ammonium salt plus this calcium hydroxide, which is your base. Ammonium salt plus base used to give you water plus ammonia plus your salt. So no worries, water is going to be H2O, ammonia is going to be NH3, salt is going to be CaCl2. That's going to be your equation. I know it's not balanced, but the thing is, you got to realize the products. What's happening is that ammonium ion is being converted into ammonia. So ammonium is a proton donor and it donated its proton to OH. That's why we're forming water. Do you get it? So what is the role of the ammonium ions? They're acting as acid because they are proton donors. And this water is a proton. This OH negative, this calcium hydroxide, is a proton acceptor. It's accepting protons to form water. Got it? Elements Y and Z are both in period 3. Element Y has the smallest atomic radius in period 3. Okay, so I'm going to list all period 3 elements: sodium, magnesium, aluminum, silicon, phosphorus, sulfur, chlorine, and argon. Now I know that across my period, what happens to my atomic radius? Does it increase or it decrease? What do you guys think? I think it decreases because the nuclear charge is increasing and the shielding remains constant. So it's gonna decrease. So smallest atomic radius in period 3, we're dealing with something over here, I think. Element Y and Z react together to form compound R. There are only 2 elements in the period 3 that have a lower melting point than element Z. So element Z, there are only two elements that have lower. All other have higher. So firstly, I know that my element Y is going to be chlorine. Why is it going to be chlorine? Because chlorine has the smallest atomic radius. Argon has a bigger atomic radius than chlorine. That's because chlorine has a van der Waals radius. That means 2 atoms are like covalently bonded and then you measure their distance. Whereas for argon, since it's monoatomic, the radius we measure like this. So for argon, we know it's incorrect, but still we measure it like this. So it's going to be chlorine. Okay. Now coming that if we just look at the graph for the melting and boiling points of the period 3, we have sodium, magnesium, aluminum, silicon, phosphorus, sulfur, chlorine, and argon. We're not going to do it. So if I start drawing sodium, then a little above magnesium, then a little above aluminum, then very above silicon, then for phosphorus, sulfur, and chlorine. To determine the melting points, you got to make sure about the number of electrons because all these 3 are going to have instantaneous dipole or temporary dipoles. So we know that we have P4 molecule and P4. So let's check for 1P and then we're going to times it 4. 31 times 4. So P is gonna come somewhere here. Sulfur is gonna be above P because sulfur has a molecule of S8 more electrons, and chlorine is gonna be below. So now that's what we've got. And then argon is even gonna be below chlorine. So if we do it like this, this, and this, you can see one thing, that sulfur has 3 things below it. We need an element that has only 2 elements that have lower melting point than it. 2 elements that have lower melting point. Phosphorus only has 2 elements below it. Chlorine has only 1 element below it. So in the entire period, if you look, that's the table for melting boiling points. And that's going to be phosphorus. In the first statement, Y came out to be chlorine. In the second statement, Z came out to be phosphorus. So we're dealing with PCl3 or PCl5. That's option D. 1 gram of each of the 4 compounds. So we have equal mass. Equal mass does never mean equal moles. Remember that equal mass does not mean equal moles. People always think that if mass is equal, moles is equal. No, that's incorrect. Of different compounds or group 2 elements that are thermally decomposed, the residue in each decomposition is the oxide of the group 2 element. The volume of the gas produced for each reaction is measured. Which substance produces the greatest volume of gas? Firstly, you know that when we decompose nitrates, for example, with calcium nitrate, we're going to produce calcium oxide plus nitrogen dioxide plus oxygen. And when we're going to decompose calcium carbonate, we're going to produce calcium oxide plus carbon dioxide. So you can see it for yourself that over here, we produce 2.5 moles of gases. And over here, we're producing 1 mole of gas only. So we're going to cut out all carbonates. Strontium carbonate. Now we have calcium nitrate and strontium nitrate. Now we need to see which is going to have more moles in 1 gram, because the substance that's going to have more moles is going to produce more gas. Okay, so for here, you got to use the formula moles equal to mass upon mR. So mR and moles have an inverse relation. You know that strontium has more mR than calcium. So strontium nitrate is going to have a greater mR. Since it's going to have a greater mR, it's going to have less moles because mass is constant. If you know physics, you know that 1.0 gram mass is constant. If one quantity is constant, you can create a relation between these two quantities. So this is going to be inverse relation. So strontium is going to have less moles because of its greater mR. So calcium is going to have more moles in 1 gram. That's why it's going to produce the highest amount of gases. Sulfur dioxide in the atmosphere can form acid rain. This occurs in 2 steps, the oxidation of SO2 to SO3, and that's catalyzed by NO2 in the atmosphere. When we do it like below, we use vanadium oxide as the catalyst, but in the atmosphere, this oxidizes it. Formation of dilute sulfuric acid. Okay, what happens is that sulfur trioxide is going to react with water to form sulfuric acid. Which statement about the mechanism of an SN1 reaction of a halogenoalkane is correct? So let's see what happens in SN1 mechanism. We have a tertiary halogenoalkane, something like this. And since it's a tertiary halogenoalkane, our nucleophile, which may be OH negative over here, is unable to attack this carbon because it has these bulky groups attached with it. So what's going to happen is that first we're going to draw partial charges. Carbon will be partial positive, chlorine will be partial negative because the lone pair is going to be more attracted towards the chlorine because chlorine is more electronegative. So what's going to happen is that this bond, this carbon-chlorine bond, is going to break heterolytically, and chlorine is going to take away the electrons from carbon and it's going to move away with those electrons. And now the OH is ready to attack this. Now this carbon is not going to be partial positive, it's going to be fully positive because now chlorine has taken the electrons. So now chlorine is going to have the lone pair of electrons, something like this, and this OH can now attack the carbon and now it can attach with the carbon. So let's see what the statement says. A nucleophile is substituted by an electrophile. No, a nucleophile is substituted by a nucleophile because chlorine was a nucleophile and OH negative is a nucleophile. Both are nucleus loving species because both have lone pairs. So one nucleophile was here and now it's replaced by another nucleophile. So cross. One intermediate is formed from two reacting molecules. One intermediate is formed from two reacting molecules. Are there any two reacting molecules from which one intermediate is formed? No. Intermediate, this carbocation is formed when a heterolytic bond fission takes place. So I don't think so, it's correct. The intermediate is stabilized by adjacent alkyl groups. That's correct. Because there are three alkyl groups in a tertiary halogenoalkane. Because there are three alkane groups. So one group, two group and three group, and you know that alkane groups are electron donating groups. That's why they have a positive inductive effect. That's why a tertiary carbocation is more stable than a primary or secondary because it has more alkyl groups attached to it. So well, this option makes sense to me. I'm going to read the next one. The intermediate is uncharged. Who said it's uncharged? It's charged because the intermediate is a carbocation, so it has a positive charge on it. The repeat unit of the polymer is shown. Three statements about this polymer are listed. So basically the repeat unit of a polymer is shown. We have, if we see the repeat unit and if we make this double bond inside, there's going to be a double bond here. So this is one thing, and then if we make this bond that's extending outside inside this. So over here what's happening is that I think that it is made up of two monomers. The first monomer is this one, HHCl. That's the first monomer. You can see it over here. And the second monomer I think is this one, which looks something like carbon double bonded carbon, H, 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 and OH. Its disposal is hazardous because it produces toxic gases when burned. 100% correct, because it has a chlorine and when it's going to get burned, it's going to produce HCl, and HCl is toxic. So this is correct. Two different monomers I used to make this polymer. Yes, I think two different because I drew two different. The monomer for this polymer is 3-chlorobutene-1-ol. Firstly, 3-chlorobutene-1-ol. Let's draw this. So butene. 1, 2, 3, 4, butene, 1 ol, and then there is 3 chloro, 1, 2, 3 chloro. Okay, so they're saying that this fella is the monomer of this. No. So I'm gonna polymerize this and make you guys realize that what they're saying is not correct. Why it is not correct? Okay. So if you attach this entire chain upwards over here, CH3 chain on this carbon, so I'm going to remove this chain and attach it on the top of this carbon because I need my carbons to be empty on the sides, and this CH2OH chain on the top of this carbon. CH2OH chain. And now if I polymerize it, you know what I'm going to form? I'm going to form CH3Cl, CH2OH, H, then CH3Cl, CH2OH, and then H, and there are going to be two extension bonds like this, and that's my polymer, which does not match the one in here. So only my first two options seem correct. You can see it for yourself. This polymer does not match this polymer. Next part. it says methanoic acid has acidic properties. That means it can donate a proton. Similar to those of other carboxylic acids, in addition, it can be oxidized by the same oxidizing agents that are capable of oxidizing aldehydes. So we're dealing with KMNO4, I think, because methanoic acid has an acidic property similar to those of other carboxylic acid, and in addition, it can be oxidized. We know that I don't think any what do you call it? What are those things called? What do you call those things? Acids cannot be, I guess, further oxidized, but they're saying that this acid is going to be, in fact, aldehydes can be oxidized into acid. Which pair consists of two compounds that will give the same observation with Felling's reagent? Okay, so Felling's reagent, we need same observation. So over here, this is methanoic acid, and this is our aldehyde, and they just told us that aldehyde and acid both are going to be oxidized. So I guess this is an acid and this is also an acid. They only told us methanoic acid can be oxidized. They never told us about ethanoic acid. And this right here is an ester, I guess. No, this is a ketone, so that's correct. Felling's reagent does not give any positive test for ketones. Which row gives pentane nitrile as one product? So for pentane nitrile, firstly we need four carbon thing, and then we're gonna add HCN or whatever thing to it, and then we're gonna make nitrile. So for halogenoalkanes, you should remember one thing, that we don't add HCN. HCN is added to carbonyl compounds. HCN is added to carbonyl compounds. For our halogenoalkanes, we use KCN in ethanol. Heat with KCN and ethanol. So this and this. Now halogenoalkane, I told you I need 4 carbons in it because I need pentane nitrile, and then I'm gonna add 1 carbon to the chain, and that's gonna form 5 carbons. So 1, 2, 3, 4 carbons, correct. 1, 2, 3, 4, 5 carbons, incorrect, because when I'm gonna add KCN to 5 carbons instead of pentane nitrile, it's gonna form hexane nitrile. Got it? Got it? Okay. An ester RCO2R is hydrolyzed in alkaline conditions. R nod and R nod are different alkyl groups. Okay. So basically we have an ester. This part and this part, they're two different groups. Now you should know that R nod is gonna be our acid. Why? Because R nod has C double bonded O R nod. So this part that's before the C double bond O is the acid part, and this part is the alcohol part. So if it's hydrolyzed in alkaline conditions, what we're gonna form? We're gonna form R nod, which is gonna be an acid, and then we're gonna form R nod, which is gonna be an alcohol. Over here, we're gonna form alcohol. But over here, the question says that in alkaline condition, what's gonna happen? The acid is going to react with the alkali, because we're doing acidic, not doing acidic hydrolysis, we're doing alkaline hydrolysis. So the acid is going to react with the alkali, and when acid is going to react with alkali, what is going to form? It's going to form a salt. So the COOH, C double bond O, OH part in the acid, H is going to go away, and there's going to be a metal attached to it like sodium or magnesium for the salt to be formed. So it's going to form a negative COO negative thing over here. So this is going to be the salt part that's going to be formed. So you just had to realize a little like technical thing over here. Firstly, this part's acid and this part's alcohol, and secondly, the acid's going to react with the alkali. Which compound cannot be oxidized by acidified potassium dichromate solution but does react with sodium metal? Okay, which cannot be oxidized? We know that alcohols can be oxidized, but only primary and secondary alcohols can be oxidized. Tertiary alcohols cannot be oxidized. So I'm looking for a tertiary alcohol here. This is not a tertiary alcohol. This is not a tertiary alcohol. Well, this one is a tertiary alcohol. Got it? So this is going to react with sodium metal because it has an OH group, but it cannot be oxidized because it's a tertiary alcohol. And well, this is a ketone. Ketones don't react with sodium metals, nor are they oxidized. Butane 2-on reacts with alkaline I2. Okay, butane 2-on. What is butane 2-on? It's a ketone, alkaline I2, iodoform thing. Good? An excess of dilute sulfuric acid is then added to the reaction mixture. The organic products of the reaction sequence are triiodomethane and M. What is M? Okay, so butane 2-on, I'm going to show what are we doing here. So this part is going to go as triiodomethane. To get this carbon is going to go for triiodomethane. What are we going to be left with? We are going to be left with propanoiodine, right? And then when we're going to add sulfuric acid to it, H2SO4, because they've written, then we're adding sulfuric acid, this propanoiodine is going to get a H plus and it's going to form propanoic acid. Okay, I know this was a brainer. No worries. Firstly, what's going to happen is that first carbon is going to go to form triiodomethane, which is CHI3, gone. 3 carbons left. Out of those 3 carbons, what's going to happen is that one carbon over here, it's going to form double bond O negative ion, but an H plus from the sulfuric acid is going to come here and going to form propanoic acid. So where is propanoic acid? This is propanoic acid. Okay, 4 reagents are listed. Which reagents, when added to ethanol, will rapidly produce a gas that turns blue litmus paper red? Blue litmus paper red. HCl is going to be produced here. HCl is going to be produced here. I guess 3 and 4 only, right? Yeah, I'm correct. Because when you add KCl to ethanol, I don't think salt plus ethanol is any reaction. HCl is also like salt plus ethanol is any reaction. But when you add SOCl2 and when you add PCl5, what happens is that you produce HCl. And you form POCl3 and then you form SO2 over here. So these are the reactions that are written in your books. You got to learn them. No worries. Okay. 4 drops of 1-chlorobutane, 1 bromobutane, 1 chlorobutane, 1 bromobutane, 1 iodobutane are put separately into 3 test tubes containing 1 cm cube of aqueous silver nitrate at 60 degrees Celsius. In each case, as a hydrolysis reaction occurs, we have water, we have this bromobutane, butane thing, and then we have silver, and then we're forming this, and this. R represents C4H9, X represents the halogen atom. The rate of formation of cloudiness in the test tube is the order. Firstly, iodine is going to form in the lowest amount of rate, time, then bromide, and then chloride. Why is this? Because C4H9 means there are 4 carbon atoms and then there is 1 halogen connected to it. So if it's iodine is going to break this bond faster. So it gets relieved faster from the carbon. Whereas if there's a carbon-chlorine bond, there's going to be more energy required to break it. That's why it's going to be a little slower. That's why iodine, Ri, which means whatever that halogen or alkane is going to be, which is iodine, iodobutane, it's going to form the cloudiness the faster because iodine is going to be given out in the solution the fastest. Because the Rx bond polarity decreases from RCl to Ri. Decreases from RCl to Ri. That's correct, I think. The bond is becoming less polar. But polarity is not what matters. Strength of the bond is what matters. Polarity is not gonna, I just realized, polarity is not gonna make the bond strong. Sorry. The bond energy of Rx decreases. Yeah, energy matters because you have to break the bond. When you gotta break the bond, it's polar, it's non-polar, doesn't matter. Okay, so F bond is non-polar. N bond is non-polar. Both are non-polar, but N bond is, for instance, I'm not sure, it has a higher bond energy. That does not mean it's polar or non-polar. That just means that more energy is required to break this N bond. Polarity and bond energy are two different things. Just because a bond is polar doesn't mean it's going to break faster or slower. Propanoic acid reacts with LiAlH4 to give organic product P. Methanoic acid reacts with organic product P in the presence of a few drops of concentrated sulfuric acid to give organic product Q. What are the skeletal formula of the two organic products? Okay, so we have methanoic acid reacts with organic product P. Okay, in the presence of a few drops of concentrated sulfuric acid to give product Q. So don't you think we're making an ester over here? And we have methanoic acid. Acid is methanoic acid. So this one cross, and what is a double bond doing there? Or is it an aldehyde or whatever? No. 1, 2, 3. No. Okay, propanoic acid reacts with LiAlH4. So propanoic acid has to be reduced. And when an acid is going to reduce, it's going to form an alcohol. So it's going to form propanol. This is propanol, this is propanol. 1, 2, 3. And propanol is going to react with methanoic acid to form methyl propanoid. This is methyl propanoid. So option B. Simple. Samples of the gases CH3Cl and Cl2 are mixed together and irradiated by UV light. So we are doing free radical substitution. Which compound is produced by a termination step in the reaction? We don't produce hydrogen in termination step. We don't produce HCl. We don't produce double bonded things in termination. So we're going to form this. Two free radicals of this thing are going to join together. We double the carbon chain in termination. Got it? Propan-1-ol is dehydrated. It's going to form an alkene by passing its vapor over hot aluminum oxide to give a hydrocarbon. Propan-1-ol is going to form propene, which is going to be this. Propan-1-ol is going to form propene. Which structural formula represents the product obtained when the hydrocarbon reacts with bromine? Now, if I add bromine to it, one Br is going to attach here, one Br is going to attach here. Look, this is the product. Simple. Alkane S has the molecular formula C4H10. S reacts with Cl2 in the presence of sunlight to produce only two different monochloroalkanes, C4H9Cl. So now, alkane S has this molecular formula. How many structures can we make with the molecular formula C4H10? Let's see. So the first structure that we can make is a straight chain alkane, which is butane. And the second structure that we can make is we can add a branch on the second carbon and we can make methyl propane, something like this. Now S is going to react with chlorine and in the presence of sunlight to produce only two different monochloroalkanes. So if I make my butane react with chlorine, I can form two different monochloroalkanes. The first is going to be but-1-ane and the second one is going to be 1-chlorobutane and the second one is going to be 2-chlorobutane. If the chlorine attaches to the first carbon, it's going to become 1-chlorobutane. If the chlorine attaches to the second carbon, it's going to become 2-chlorobutane. And if I do it with my methyl propane, if my chlorine attaches to the first carbon, it's going to form 1-chloro-2-methyl propane, and if it attaches to the second carbon, like if I have a new one, so if I place it over here, So this is going to become 2-chloro, 2-chloro, 2-methyl propane. Got it? 2-chloro, 2-methyl propane, 1-chloro, 2-methyl propane, 1-chlorobutane and 2-chlorobutane. 2 monochloroalkanes possible for the butane and 2 monochloroalkanes possible for the methyl propane thing. Okay. Both of these monochloroalkanes, we don't know either it's this one or this one, are treated with hot ethanolic KOH. They both produce the same alkene T and no other organic products. So if I treat these two first with the hot ethanolic KOH, what kind of reaction is going to occur? Elimination reaction is going to occur. And if elimination reaction is going to occur, that means a double bond could form here. And for this chlorine, a double bond could form here as well. So this will produce but-2-ene, and this is going to produce but-1-ene. And over here it's written that they both produce the same alkene T. That means we are not dealing with, this is a difficult question, we're not dealing with butane. Why are we not dealing with butane? Because the monochloroalkane that we are forming with butane can form two different alkenes, but-1-ene and but-2-ene. But they're saying that only same alkene should be formed. Whereas if we look over here, a double bond can only form here. This is going to be 2-methyl propene, right? 2-methyl propene is going to be this thing. And if I look over here, a double bond can form here. If it forms here, it is going to be 2-methyl propene. And if the double bond forms here, it is still going to be 2-methyl propene. Look, if a double bond forms here, it's going to be 2-methyl propene. But if it forms here, it's still going to be 2-methyl propene. And if it forms, if it erase this, it's going to form here, it's going to be 2-methyl propene. So no matter what we do, we're forming the same kind of alkene. So that's why it's going to be this alkane that we were initially dealing with. Now, what is produced when the alkene is treated with hot concentrated acidified KMnO4? So they're saying that if you have this thing, this alkene, and you heat it with, this is the alkene now we're dealing with, and you heat this alkene with KMnO4, hot concentrated acidified KMnO4, what will it do? It will oxidize this alkene and it's going to break off the double bond from between. And since this carbon has 2 hydrogens attached to it, whenever a carbon that's broken in a double bond has 2 hydrogens, it gets converted into carbon dioxide. And this carbon right here is attached to, oh well, I created another bond, I'm sorry for this bond. Okay, this carbon right here is attached to 2 alkyl group, 1 alkyl group on this side and 1 alkyl group here. So it's attached to 2 alkyl groups. So this one right here is going to form a ketone. This is a carboxylic acid. No, we're going to form a ketone. This is a ketone because over here the oxygen is in the middle. So it's going to be option B. Why option B? You can see it for yourself. We're going to form a ketone here because this carbon attached to 2 alkyl groups and this carbon attached to 2 hydrogens. Including structural isomerism and stereoisomerism, how many isomers are there for C2H2Br2? Okay, C2H2Br2. This is first going to form 1 cis, 1 trans, 1 cis, 1 trans, and if we do this, HHBr, then no cis, no trans, right? Because carbon is going to be attached to 2 bromines, that's not going to form cis trans because for cis trans you should have 2 different groups attached to the same carbon. So that means 1 cis, 1 trans and 1 this thing. So that's a total of 3 isomers. This, and this. Cis trans for this thing and no cis trans for this thing. So that's a total of three isomers. Which compound exhibits stereoisomerism? So for stereoisomer, what we're looking for? Either we're looking for a chiral carbon or we're looking for a double bonded carbon that has two different groups attached to it. So you're going to draw each one of them. 1,1-dichloropropene. Chlorine, chlorine. And if I just fully draw it, you can see it for yourself. No cis trans, no chiral carbon, and double bonded carbon has same groups attached to it. So this one's not possible. 2,3-dichloropropene. 2, 3. Well, if I look here, I have no chiral carbon. This carbon attached to two hydrogens, so there's no chiral carbon, and the double bonded carbon has two hydrogens attached to it, so no. 1,2-dichloropropane. 1, 2, 3. 1 chloro, 2 chloro. Yes, this is gonna show cis trans. Why? Because you can spot it for yourself. If you've studied enough, you should know this thing. Can't you see that this carbon is chiral? Above it has one chlorine, below it is one hydrogen, on the left side it is CClH, and on the left side it is CH3. So it is four different groups. One group, two group, three group, four groups. So it has four different groups. Got it? So this is correct. But we're going to go with the third one as well. 1,3-dichloropropane. So propane means carbon, carbon, and carbon, and 1,3-dichloro means chlorine on first, chlorine on second, and then 1,3, chlorine on the third. Well, again, no chiral at all. See it for yourself. There's no chiral carbon anywhere in this structure. Nothing that we can think of. No double bonded carbon that has different groups, no chiral, so let's forget it. Okay. The mass spectrum of CH3Cl shows a molecular ion peak at 50 with a relative abundance of 18%. Other peaks are present in the mass spectrum. What is seen with the mass spectrum at the value of 52? So this is an M plus peak, and this is an M plus 2 peak because it's occurring at 52. You know that chlorine has 35 isotope and chlorine has 37 isotope. This peak, the M plus peak, was because of the chlorine 35 isotope, and M 52 peak is going to be because of the chlorine 37 isotope. 35 isotope is 75% abundance, and 35 isotope is in how much abundance? 25%. So if 75% abundance gave you a peak of means 18%, gave you a peak at 18%, then the 25% abundance is going to give you a peak at X. Calculate the value of X. 25 into 18 upon 75. 25 into 18 upon 75. 25 into 18 divided by 75, and that gives me 6. So I'm going to get a peak at the abundance of 6, because that is because of the, I'm again telling you, that is because of the chlorine 37. And you should keep in mind that 18% was because of chlorine 35, which is in 75% abundance, and 37 is because of the chlorine 37, which is in 25% abundance. Got it? That's how you do it.